Goed, goedemiddag, dames en heren. Welcome to this seminar session. I would like to welcome Jan Beirlant from the Catholic University from Leuven. Jan is an old friend of the department, and he's going to talk on non-parametric Keir models for through tail estimation.
Thank you very much. Now I'm proud also to be now member of the department. So I proudly put University of Stellenbosch. Yeah. So last year it was still Bloemfontein, but that's now gone. So, okay. So it's work that I have been working on last 2 years at a slow pace with Martin Blad, who is a young professor at the University of Copenhagen, and Ingrid van Keilholm, who is rather well known in survival analysis. She did some work early on this subject with some postdocs in Leuven. And when I saw it, I said, oh, this is interesting. We could do something else, the same subject. So first I'm gonna introduce what is the Keir modeling applications to get you motivated. Stay with me. And then I show the solutions that are there in literature. Today it's only univariate, so simple things. There's some solutions already for regression settings and so on, but it would be a bit too far-fetched. Asymptotic results are very difficult. Last year, my 2 months in University of the Free State, I spent completely on it. And I'm still not 150% sure that it is correct. So I'm worried. But okay, we have a lot of simulations which show it works somehow. What we propose. We have a case study about pregnancy, duration and stuff, times between pregnancies, to be correct. And we conclude. So what is it? So I'm talking about the survival time of a subject. Classically in survival analysis, that's what we're thinking of, but I'll give other examples. And the Q rate, okay, is the probability that the survival time is infinity, okay, which is impossible, so to speak, but you have to interpret this as, okay, a person is cured, is non-susceptible for an illness, for instance, okay? Person will die, but not because of the illness that we're talking about, that is under study, understand? So we call it t equal to infinity, okay? This is what it means, right? And so we will gonna estimate little p, which is a number between 0 and 1, perhaps 0, but okay. And, perhaps 1, yeah. But so if nobody can be cured, everybody is susceptible for an illness, then it will be p equal to 1, okay? So that's what we're gonna estimate. So the distribution function of what observes, okay? So the distribution function ft, the probability that your random variable is more or equal to little t, some specific value, you put it up in 2 parts, given it's smaller than infinity, so susceptible, times the probability of being susceptible, plus the same thing when it's not susceptible. Okay, so, but of course the second term is 0, because if you are non-susceptible, okay, you will survive longer, it's an infinity, so the second probability is 0. So you have like a sub-distribution. So ft is p times the distribution function of the susceptibles, okay, that are non-cured or susceptibles. Okay, so this is the problem. So if you have an estimate of f, okay, it will not go to 1 in case there's cured part of the population which is curable, okay, or which is cured, which is susceptible, non-susceptible. Okay, and this is how we get to it. So this is important. Ft is p times f0. F0, the distribution CDF of the non-cured subjects. Okay, the susceptible ones. Examples, except for the classical survival setting, So we think of in economics, the duration of unemployment. Okay. So how long are you unemployed? Of course, some people, and there's a big proportion in Belgium, for instance, about more than 30% will never work. Okay. So this is an application. So this is proportion, and we were going to look further. Okay, I said we're going to estimate P. This is in this field, the item, the subject of the study. But I want to go a bit further. Look at the distribution of zero. Can we know something about this distribution? Okay, the literature up to now doesn't want to say too much about it, but people are interested in F0. How will it look like? Okay, sociology, the age at which somebody marries. Some people never marry. Okay, can happen. So this is like curable in that setting. Okay. Or has a child. Some people don't want children. So what is the proportion in sociology? Criminology. I was teaching in Leuven a long time to first-year criminology students. Okay, very important subject there is how long people can stay out of prison. Okay, once you were in and you have enough of it, you will never come back to the judge. You have been cured. Okay, and you are at infinity in that subject. You understand? So this is also quite important, I would say, to estimate that P. Insurance, time until default. Hopefully very long. Okay. High proportion of curables. And education, very important to the professor here. Time to solve a certain problem. P infinity, that the students will never solve your problems. Or some students never solve your problem that you made too difficult, for instance. Okay, what is your little P in your setting, and so on and so on. You could think of many. So this is to make you, whatever field you like, choose one. That's what we're talking about. Now, even the problem would be difficult enough, it's becoming more difficult because at a certain time you have to study and you stop gathering data, and there are people who are still on the study but are still sick. Okay, so the length of the cure is centered, as we call it. Random right centered is the assumption here. Okay, some people are still staying out of jail, but yeah, you stop here, you look at your data, certain moment, you make the study, and then a person who will fall back into jail the next month, okay, you don't know, because she's still in the study. Okay, so that time until next visit to jail is censored. Okay, this is a main problem, but in mathematics, a lot have been done about this in statistics, how to solve those problems. But we have two problems. Okay, the problem is that cured individuals, the T infinity ones, are all censored. The ones which are interested most are, of course, by definition, in that set of censored ones. So you have to disentangle those in some way. Okay, so censoring the model is, so you observe the minimum of the times your random variable you're interested in, big T, but you have a censoring random variables, big C. This is the classical random right centering model. Okay, you observe the fact if a person is still in the study, but being censored or not, that you know. The indicator delta, which is 1 if T is smaller or equal to C, so it's not a censored one. Okay, person is back in jail before my time I study, so it's a delta 1 is non-censored. Okay, this we have complete information. 0 means delta equal to 0. Okay, it's still on the way, but okay, it can be when delta is 0, it can be a T infinity person or subject, or not infinite, finite, but being censored. So this is the problem. And at first you would say, however, can I ever solve this problem? Yes, it's not a simple problem. Okay. So the distribution function of what you observed, which I call the Z's, the minimum of T and C, The survival function is, of course, the product because of independence assumption between T and C of the survival function of T and the survival function big G of C. Okay, this is the notation. All right. Good. So for when you have random right censoring, there's a classical solution to estimate non-parametrically the survival function of the CDF of the times on the study. Okay, this is the Kaplan-Meier empirical distribution function, big F hat. Okay, so when you put a hat, when I put F hat is the Kaplan-Meier. And at a certain solution, one of my solutions, there will be another Kaplan-Meier, but it will be somewhat different. We'll talk about that. So I also use the notation of the ordered data here. And just put my pen here. The ordered data, the smallest one, Z1, n until the maximum ZNN of my survival times. Okay. And there is an estimate already from 1992 in Biometrica from Muller and Zhu, which is nothing else for P. P and hat is the Kaplan-Meier in the maximum observation. You understand? Because the maximum, okay, goes to the endpoint of the distribution. Okay, tau 0. Hopefully, if the censoring is not too strong, you will go to tau C, okay? F0, sorry, tau 0. So the endpoint of F0 is, I will call tau 0. Huh? So the estimate was P, so F, let me go back to explain the estimate. Here you have it. So F is estimated by the Kaplan-Meier, the left-hand side here is estimated by Kaplan-Meier. You want to know P. So if you take the maximum in T, for T, F0 in the maximum, okay, should go to 1. But the closest you can get to 1, you understand? For F0. But now comes the problem. If the censoring distribution has an endpoint which is smaller than the endpoint of F0, yes, let's call that tau C, the endpoint tau of the C distribution, the censoring distribution, which cuts your realizations or observations. Yes, you will go to P times F0 tau C, not tau 0, not the endpoint of F0. And this is called insufficient follow-up. So it has been shown, that's the main, that this estimate is, oops, P and hat is consistent, sorry, in probability instead of distribution, of course, if and only if the endpoint of the distribution F0 is not bigger than the one of the censoring distribution. Because otherwise your estimate is too low. You will have a bias. Okay. You will not go to P, you will go to P times F0 tau C. So that will be, so I hope you understand this, if I'm clear enough. This is the problem. So it is a consistent estimate, if and only if, yeah, it is under sufficient follow-up, as it is called in survival analysis, sufficient follow-up. So if your censoring is too strong in some sense, you have a problem here. You have a bias. Okay, you're too low with little p estimate. Okay, can we get rid of that? So the first solution, well, why are people in extreme value analysis? Go now to extreme value analysis, because that's tail estimation in the title. Because we're using the maximum of my data, sensor data. So there's a nice theory about this. There's been a lot of results on censored random variable, censoring, and extremes. Okay, so that's why this group of people working in extreme value are interested in this. And in fact, the first paper to get rid of it, well, with the purpose of trying to get rid of this insufficient follow-up problem, has been done only recently in a paper by Escobar-Bach. He's French, he's not Spanish, and he's not German like Bach. Austin, he's French, Escobar-Bach. In fact, he was a student of Yuri Hugebeur, PhD student in Denmark. Yuri has been in the department for a long time ago. And Ingrid van Keijeren. So he was for a couple of years postdoc in Leuven, and then they developed these solutions. Okay. And they have some assumptions, okay, and they had a smart way of trying to get rid of the problem. So, not empirically, but in probability, they looked at something to get rid of the bias, rather than F0 tau C, F tau C, which was P times F0 of tau C, is the solution, is the where you go to in insufficient follow-up. And they try to adapt it with something to get the bias smaller. Okay, to alleviate the bias that you get in the problem anyway. There's no way to escape that. But you can try to get it small using extreme value methods. That's basically what the talk is about. So let me go to extreme value analysis, one page. So what we are doing in extreme, what we assume in extreme value analysis is that we have the so-called peaks over threshold assumption, under which maxima behave appropriate to a generalized extreme value distribution. Okay, there's a nice asymptotic distribution, and we can do statistics on extremes and extrapolating out the data under this assumption. Okay, so I assume on F0, okay, the assumption is on the distribution F0 of the non-cured ones, the distribution of the non-cured ones, F0 is the distribution function. We assume that there is a nice peaks over threshold result assumption. And this means that this ratio means basically that the probability that a time, okay, minus a certain threshold little t being bigger than v times a certain sigma function t, given that you consider only the data above a certain high threshold, that this for t going to in t tau 0, the endpoint, okay, that you go to this what we call GPD, generalized Pareto distribution. If gamma is 0, this is just a simple standard exponential distribution. If you take the limit in the right-hand side here, yes, this is E minus V for gamma equal to 0. Okay, so this is it for gamma equal to 0. Otherwise, gamma positive, you have a Pareto distribution. So this is what I write there. Can show that this assumption, pot assumption or condition is true if and only if for gamma positive, you have what we call a Pareto type distribution. It is a simple Pareto distribution, t to the minus 1 over gamma, times what we call a slowly varying function, take of a constant, doesn't vary at all, it's constant, it's slow variation, but a constant plus something going to 0 at infinity, a logarithm goes to infinity, very, very slowly, extremely slowly. So this is the property that LTV over LT for t going to infinity goes to 1. Okay, if you go from 1,000 to 2,000, from 1 billion to 2 million, it's almost 1. In the logarithm, it's the case. So this is gamma positive. So the first solution by my colleagues Escobar-Bach and Ingrid van Keijeren, they looked at that case. I don't think this is really applications, survival analysis, and the applications that are shown of getting at one doesn't observe too much such distributions, very heavy tail distributions. Okay, but okay, it's a nice workable assumption. Okay, mathematically, it's much simpler than gamma zero, which is a big basket of distributions ranging from Weibull, of normal, gamma distributions. Okay, all these kind of things are in there. And for those, the peaks of a threshold mean that excesses over a threshold t high enough behaves exponentially. Okay, it's of course a very nice result. It's kind of universality for all those distributions, but the fact that always the exponential distribution has to approximate all those elements from that set of distributions will make that it is not always so appropriate, not always a good approximation. In the limit it is, but how big should the threshold be for this to be acceptable in practice? This is the problem. But anyway, so I think for survival analysis, we should not, I would accept that, or I would think that gamma equal to 0 is more appropriate. Okay. In extreme value, we also have ways to take that all in one set, one type of analysis. Gamma positive, 0. I now forget about gamma negative, yes, which is finite endpoint distributions, like the uniform and that kind of things, yes, that we can do it in one analysis. But then I have to estimate gamma. And this is really something extra to be done, which the problem is already difficult enough. So we split it up in Gumbel, Pareto, and so on. Okay, this is what I'm going to do. Later, we could do it in encapsulated in one big model, but this is not done yet. So under this assumption, which is broad and could help, okay, mainly the first is quite specific. The Pareto types, the gamma positive is quite specific. Okay. Ingrid van Keilogem and Escobar have given this solution. They adapted that, and then they estimate F by the Kaplan-Meier, of course, and tau C by tau C, the estimate by the maximum observation. What else could you do? Okay, and probabilistically, this expression, they prove purely probabilistic, pure metristic calculation, not with expected value, whatever, just without heads on, without random variables. So the expected value is shown to be closer to the unknown P. For tau C going to infinity, closer than P head was to the F in tau C, the first term here, this one would be further away from the unknown P. So they claim that theoretically the bias is smaller, but you have to put F, replace F by F hat, tau C by the maximum observation, which is censored. Okay, what's in between that last step? That they don't write anything about the bias. So you have to simulate. It's quite complicated to do that. Very smart technique in some sense, because the gamma is gone. So you don't have to estimate gamma. Even if you're in the Pareto case, where you assume a certain positive value of gamma, you don't need it. So it's a technique to lift that out. People who are working extreme value, this makes you think of Pickens estimators that are there. You use a few data points and you play with it. So basically, and they use a y. The y is in there, or whether, yeah, y is a number between 0 and 1. They have to choose it. This is another problem. It's very nice that they don't have to estimate gamma, but they have to choose a y. So you look at the maximum. You take, for instance, y a half, a number tau C, or the maximum ZNN, maximum observation divided by 2, and the max, okay, and then y squared, you see 2 in the expression, then the maximum observation divided by 4. So they look at 3, 4 observations, the maximum divided by 2, the maximum divided by 4, and they play with it, and there's something better coming out in theory. Okay, we're going to see in the simulations how it works. So when you see this, okay, the first thing you do, why only using 3 data points? Or values, the Kaplan-Meier in 3 points. why not all between something and something, you know? Why throw away so many observations? So will that help? That was in fact the question. But okay, you have to be able to do it. And then comes our solutions. I like empirical plotting. Last year I talked about probability plots. I'm using them again in my seminar last year. So Pareto behavior. You will see, okay, if you plot, if you would have the possibility of plotting F0 hat, an estimate of F0, which I don't. I only have an estimate of F with the Kaplan-Meier. Okay. Then if you take log in certain values against the minus log of the survival function of 0, then you will have a slope 1 over gamma. And then you should have a linear shape, log, linear shape, and the slope will be 1 over gamma. If you think F0 bar, 1 minus F0 is t to the minus 1 over gamma. You take a log, you get 1 over gamma. So your slope will be 1 over gamma, and it should be linear. So this is a way to verifying in a goodness of free way that you have Pareto behavior, if this plot would be linear, okay? But how does it help me to estimate P? Well, F0 hat of T, I can estimate it by F hat divided by P, because F was P times F0 from the first slide. One of the first slides. Okay, my first formula was F is P F0. So I just substitute. If I would have a guess of P, I can replace F0 in my plot by F hat, Kaplan-Meier, divided by P. But of course, I don't have a guess. I have to estimate. So I want linearity. If it's linear, I can make least squares on the plot, on the probability plot. All right. I will show examples with simulations and a case study. But I also have this P, this gamma. In this case, I have to estimate gamma. Okay, so I have two parameters, the P and the gamma. Because I'm stuck with Pareto, and the Pareto index, as we call it, or the extreme value index in this case, is to be estimated too. So you have a plot which starts to become linear, hopefully, from a certain point on, the top K points. You assume, hopefully, well, if you see linear behavior, okay, you're going to make some linear regression on this QQ plot on the top K points. Okay. And you have least squares with two parameters. Okay. And once you have solutions, the optimization of that surface, which is rather flat, turns out, yeah, in P certainly, then, okay, you replace the top parameter, the expression for the plot, you replace your estimates, and then you can verify, you can show the end how good that plot is, how linear that plot is. Okay, this is for Pareto. Okay, so this is just looking, hopefully helping us to verify if something would be Pareto. Okay, but Pareto, I said again, probably in survival analysis and these applications, not too much at stake. You know, it's not a good model, very heavy tail. It's good in diamond digging and stuff. Losses in insurance, lost data, but we are not talking, we are talking of duration data, right? Most of the time. So I don't, okay, mathematically is the most simple case. But in the Gumbel, rather than going immediately to the full Gumbel setting, as Escobar Bach and Ingrid did in the second paper in Biometrica, the first one was in GRSS a few years ago, then a year or two later, they had for the Gumbel a similar adaptation, which I saved to you. Okay, quite complicated, but also a similar kind of approach. They had another solution. So we started first with some specific examples of which you can make a probability plot again, Weibull distribution, log normal distribution. Okay, for a Weibull type, we only look in the tail, so I don't want all the data to be used. Some setting of which I hope to have some nice structure to detect it with probability plotting. So a probability plot for the Weibull, we teach that to the students in the prime value analysis, the log of the data against log of minus log of the survival function f0. Again, I don't know what f0 is, but I can replace it by f divided by p. And for f, I have an estimate, the Kaplan-Meier estimate. And again, I do the same thing. Now the slope is the tau parameter of the Weibull. And once I have an estimate for p, which is sitting here, you see in the optimization, I have a p two positions, and I have a beta, the slope in this probability plot, which is tau in this case. Okay, then I can see if it's really linear or not to verify, to look at the kind of graphical goodness of fit. Okay, and log normal, everybody knows that best of all. So the log of the data should be normal. So the standard normal quantile function phi minus 1 in the data, in the probabilities, f0 of an observation t. And again, you have this p and do these squares. It's a bit hidden. I'm sorry for the right-hand side, which is the least squares problem. And again, log normal goodness of fit plotting at the end when you have a solution for p. Okay, the notation is when it's in the log normal setting, I call it p hat L. Okay, and the one before it was p hat W for Weibull. And for the first one, it was Pareto. I called it p hat P. Okay, so it's like guessing what kind of distribution I could have. Classical distributions, Weibull, log normal, Pareto, and which one fits best to the data. And once we found one of these three fits well, you have kind of an estimate of it. Okay. Now, I have another set of solutions. Well, but first, in general, it's always of the type, whatever case of the three I consider, you could do this with more or different distributions with least squares. But and this is what Martin, the guy from Copenhagen, did. He said, well, Jan, I did some penalization on P. I don't want to go too far away from P hat N. The solution, the first bias solution from Mahler and Zhu, okay? Which is very simple. The Kaplan-Meier in the maximum observation. Okay, so we added the lambda, P minus P and hat squared. Okay, that helped him. I don't have a feeling for optimization. He has that in his fingers and his elbows. He adds that and it works. Okay, and it works much faster. Okay, have a solution. It was too flat, the surface optimization surface, without this penalization. Okay, and so this is the more general way of writing it down, what I said 3 times differently, but sorry about that. But we have to penalize. We have the second set of solutions. And this is now for the Gumbel as a whole domain. Whatever, if it's so, it should work. Whether it's Weibull or normal gamma, it doesn't matter. But there's much more in that class than those 3. Okay, something that should work. So again, I recall the pot technique for f0. So we assume for f0, this means it is the probability that the excesses are bigger than u times some sigma scale parameter, given big T is bigger than little t, that you throw away all the data below the threshold, little t, but it's f0, eh? So t is being smaller than infinity. We have to add this. So if you work with pots directly, with the definition of pots, practice, this means you take a threshold. What we always do in extremes, in Portugal, they call that a port technique, random threshold. You take the k plus 1 largest observation, it's random. So this is the Zn minus k comma n here. Okay, and you take any of the data above that one. So you throw away all the ones which are smaller than my random threshold. You only keep the ones above, and you look at the excesses, Zn minus j plus 1, j running from 1 to k, the j largest, with j smaller or equal to k, compared to the k plus 1 largest, Zn minus k comma n. Those are the excesses. And you can look at the product limit estimator or the Kaplan-Meier estimator, as we call it, F hat K. This is the second one that I'm using, only on the excesses. I'm looking at the Kaplan-Meier on the excesses, and I'm doing more or less the same trick as before with least squares. Okay, but now I call it pi rather than p because it's a different setting. It's not on the whole data set. It's on the excesses over one. Okay, and it's conditioned on the fact that you're above those. Okay, but it's the same trick. Yeah, and the pot technique says, the pot assumption says that the excesses are conditionally will look like an exponential distribution. In the Gumbel case, E minus U, survival function of the exponential. So it's an exponential QQ plot or probability plot you're using here. It's easier than one before. It's the data, the excess itself, against the exponential scale, minus log 1 minus f, 0, which I have to replace by the Kaplan-Meier of the excesses, not of all the data, only the excesses, yeah, divided by something which is substitution for the letter P, because it's not P, because it's conditional on. It's not the same P as before. Okay, we are conditioning on T bigger than little t, or above some threshold. But you get a solution, 1 minus P hat, pi hat. But of course, of the conditioning, you have to reconstruct, and you bring it back to the unconditional scale at the end, which makes it a last step. You have to do times 1 minus the Kaplan-Meier of all the data in the threshold, K plus 1 largest, to get it back unconditional. All right. And you can have a second solution, do the same for the Fréchet case or the Pareto type case. But then you have to take logarithms and you do the same, but in logarithms. It's the same as before, as the one before. But for Pareto, if you take logarithms of a Pareto, you get an exponential type of. So then you're back in the preceding case, more or less. It's basically the same. So once you know for the Gumbel, you know how to do it for Pareto after taking logs. So this is the same approach, again with penalization, also in the preceding one with penalization. So if it's for the Paretos, they have two solutions. The P hat P, Pareto, and the P hat F now. We call it F because of the Fréchet. People call it also this Pareto type set of distributions, the Fréchet domain. So these are the second solution that you will see in the simulations for that case. Okay. So a lot of we have five. Well, we have five estimators, but working only for different cases. Right? Two are for the same situation, the P and P and P and F. Now, I was able to do a bit of asymptotics. Okay, I assume people extreme value. It's only one page. I don't give you the whole result. It would take 3 pages, and it's horrible to read. We assume that the F0 distribution behaves whether like Pareto. It's only for the first solution, by the way. So I don't have asymptotic solutions or any result for the ones with the excesses, the last two solutions. This is horrible. I tried that one too, but I gave up. I don't know how to do it. So we assume that the F0 survival function is of that kind with this S star I had before, Pareto, Weibull, or log normal. That's basically it. And we assume that and here it comes, that the censoring distribution, which ends at the notation tau c, is kind of tau c minus x for x going to the endpoint tau c to some power, and gamma c is negative. So for instance, if gamma c is -1, this is the uniform distribution between 0 and tau c. Okay, but you can have different powers, all gamma c negative. I should have, yeah, it's mentioned. So I will only show you the information matrix. Because this is, so the asymptotics that we have explains why you need regularization and what sense. So it turned out, after all this computation, theoretical computations, you see that the first line and the second line, except for this last, if you forget about this, I has determinant 0, because the second line is A times A to C of the first line. So I is not invertible if there's no lambda, if there's no regularization. Okay, so this is nice. It explains why that Martin's intuition was correct, okay, mathematically. And it also says how you have to choose. The asymptotics tells you theoretically how you have to choose lambda penalization. So if you are a certain k, if you use, say, k over n, 20% of the data, k over n is about a certain value, you need to choose a constant that cannot go to 0. So some positive constant c lambda. This is asymptotic approach, huh? Times k over n to the -2 gamma c. So -2 gamma c is positive, but okay. In practice, not useful because I don't know gamma c. I assume that there is some gamma c, but I have already trouble with gamma and with p. How would I know gamma c? You know, just like, that's why I stop here with asymptotics. So we know why and how you have to choose your penalization. Well, how? It's a theoretical approach. Otherwise, there's no I minus 1. Okay. So now the simulations. Then we are most all done. So first, we have 10 settings for simulations. Exponential. Okay. With the first one is with sufficient follow-up, and the second one with insufficient follow-up. Okay. With a uniform random variable between 0 and 3. It is quite strong. So your data comes from an exponential, but you censor them with 0, 3 uniformly. It's quite strong, I would say. Okay, the k that we choose is almost all the data. Because why don't we do that? Because exponential is very nice. The pots are is not in the limit going to exponential. It's exactly equal to the exponential. So we know that this should really behave well for all the data, using all the data in our extreme value approach. So these are the box plots. The first two, the first one is the left one is always the one of Mahler-Zoo. Just take P hat n, the Kaplan-Meier in the maximum observation. Then the one of Escobar-Bach and Ingrid. And the last two are ours. Okay. The Gumbel, and it's a Weibull, exponential is a Weibull, special Weibull. Yeah. So the first solution, and the third column, and the fourth is the one because it's a Gumbel approach with the excesses. So there's sufficiency, there's no insufficiency, no case, there's no problem. So we do all four do as root. It's the log of the mean square error. Right? It's the log that you see vertically. So the lower the better. Okay, in the box plots. For P 0.9 and the right hand side is 0.95. Okay. But you see, as soon as there is insufficiency, we start to do better. So there was some gain here by the solution of my colleagues, and you do better and better with the last solutions. Okay, smaller log mean square error. Then we have log normal. Insufficient is sufficient. The second one is more insufficient than the first case, than the first line. You see similar behavior. Okay. So we can improve more using more data. We improve more on the solution that it was existing in GRSS. Weibull, similar. Then we have Pareto, simple Pareto. The first one, no insufficiency. So because you have a Pareto that you center with an exponential. So they both go to infinity. Right? Both distributions end at infinity. So there's no finite endpoint for the censoring distribution. All four are as good as the others, okay? No winner at all. And the second line, this is spectacular, I would say, okay? As soon as there is insufficiency, you go down here quite a bit, show that, okay? We are proud of this. Now you think we are happy, but then comes a more difficult case, a Pareto, the last two cases. Okay, so we are doing worse. Bookplot is wider. This is a burr. So we took K 20% of N. Okay, a burr distribution, which has a, now I'm talking for the extreme value specialists. It's a case with a, which is difficult in the sense that this distribution tends to the simple Pareto distribution quite slowly. The distance from a simple Pareto is quite large. Okay, the second order behavior is bad. Okay, the beta tertius is about it's 2/3. So this is already quite difficult in extreme value. And the second part, when it's even better, it's a bit better. Okay, but the first one, the results were not so good. So it has to do, I'm sure it has to do with the choice of K. And I asked Martin to look a bit more careful in different choices of K rather than, so there is a difficulty here of choosing K, where is the good K here? Precedingly, with the page before, we don't have that problem, but because it is strict Pareto. So we take K equal to the sample size, N. It's good. There's no problem. We know it has to go linearly, the plots all the way. Okay, and the excess approximation is good all the way, using all the data. So we know there's no bias problem coming from there. At the last position, you can have a bad bias in the estimation because of the choice of K in this bird. And then my example, it's a Norwegian medical birth registry example that Ingrid gave us. There's a big sample size. It's a registry for whole Norway. And it's a time between the first and the second birth. So what you're estimating is the probability, the proportion in the population of ladies who never have a second child. Understand? So who finish with one baby, okay? Obvious cure corresponds to mothers having only one child, ultimately. Whether a mother is cured from having a second child or merely right censored is a delicate feature. This is really the problem here, which is a difficult problem. There's no simple solution. We try to do better than what was existing, but it's a problem. So this is the Kaplan-Meier, but 1 minus the Kaplan-Meier plots, the classical plots. You see it never goes to 0. It stops somewhere about 25% somewhere is the percentage here that we are estimating in Norway. 25% in Norway don't have more babies than the first one. Okay. So the horizontal line here, yeah, is the Kaplan-Meier estimate, the Muller-Zoo estimate. Okay, I don't know if there's a lot of insufficiency here, strong or small insufficiency. Okay, but we have estimates. The Gumbel solution, here's the Gumbel plot. Okay, it's quite linear all the way. Well, using 50% of the data, top data. Then our solution, which is in blue dotted line, which is also a bit almost the same as the Muller-Zoo solution estimate, the simple naive estimator, I would say. But that's each time the case. Each time we have a case which is close to the truth, yeah, the Gumbel fits in this case, then it's close to the non-parametric, simple non-parametric estimate. In fact, Escobar-Bach and Ingrid have now a paper where they produce a test of sufficient follow-up. And the test statistic is nothing else than the difference between an estimator and the original estimate squared. That's their test statistic. So this makes us believe in this case that there's not much of insufficiency. Okay, but who knows? Okay. So the Gumbel probability plot is quite linear. You see So the different columns is when you take different choices of k. The smaller k, yeah, the third column is only 2.5% of n. So you're using only very few data points at the end, yes? Then it becomes more difficult, this probability plotting, as one can expect. The Fréchet, yeah, I could get on it. I have it on a separate sheet, but I will not do it because time is up, yes? The Fréchet is not so linear, so the Fréchet solution for that is this dotted line here, the red dotted line, is way off. Okay, it doesn't fit so well. So the Fréchet or the Pareto does not fit so well. Okay, we believe there's a next page with log normal. The log normal fits the best. So we have like a fit visual for the moment, no real test. Okay, and an estimate of p, which is close to p and head in this case. Now, if this is the case study for which we have to defend our paper, if it's, yeah, we're treating insufficiency, and a lot of insufficiency, that's why we produce insufficiency, that's the last page here, okay? We modify the data. We put more and more data with a delta equal to 0. So we say they are censored, okay? And we see how long our estimator withstands the proportion, the percentage of insufficiency that we produce. And that's the blue dotted line. The one of the full line here, as horizontally you have the percentage insufficient follow-up percentage. Okay, the estimated 25% more or less is there, horizontal line. Yeah, and the yellow full line is what happens with the estimator of Escobar, Bach, and Van Keilham from GRSS. It falls down. Okay, it goes, gives up. Ours keeps up until 12-13%, which stands this extra insufficient. So this is like some extra news that we believe shows some of the good points of the technique. Thank you very much. Yeah, sorry for being so long. Okay, sorry. Yeah.